Quick housekeeping today. The chat's turned off for today's session, so please use the Q&A panel to send your questions. We'll work them in as we go. And you'll receive a follow-up email with the reference material used in today's presentation. Before we dive in, let me introduce our speakers. Mike Podd is our territory manager based out of Burlington, Ontario, Canada. Mike's been in the HVAC and refrigeration trade for 40 years, 18 installing and servicing equipment, and 22 years with Parker Sporland. We're also joined by Paul Chambers, an applications engineer with an emphasis on training. Paul earned his Bachelor of Science degree in Engineering Technology from Pittsburgh State University in Kansas, where he dual majored in Mechanical Engineering Technology and Automotive Technology. All right, then, let's get started. Gentlemen, take it away.
All right, thank you. Paul, can you unmute and call up the screen, please?
We'll do that.
Excellent. Well, thank you everyone for participating today. Appreciate you giving us your time.
Absolutely.
Okay.
So yeah, as John so warmly welcomed us, we're going to be talking about head pressure controls today. I think in the importance of setting those, I think is really where we want to dig into. But we'll start with just a really quick question for Mike here. And what is head pressure?
Well, head pressure is the high side pressure on the refrigeration system, and what we need to basically looking at this typical refrigeration system, this would be sized for that evaporator load on a design day. So for the basically for the hottest day of the year, all of this equipment needs to be sized appropriately so that we can do the work, satisfy the evaporator load on the hottest day of the year. So in doing so, everything is balanced, and we need sufficient high side pressure to move the volume of refrigerant through the expansion valve and the evaporator to satisfy the load. And the condenser is sized to condense and carry that liquid, condense the liquid so that it can be carried to the expansion valve and do the work. So on a design day, that will typically be your hottest day of the year, right?
Okay.
So what happens as temperatures go down is that now your condenser starts to become larger than required. And now on an air conditioning system or a refrigeration system that uses an indoor condensing unit, the condenser is always going to be in the same ambient conditions. But when the condenser is outside and something that was sized for 120 condensing is now working at 80 condensing or substantially lower, that condenser is now oversized for the application. It only uses a portion of its condenser surface to condense, and then it further cools and lowers the pressure of the refrigerant. So now we no longer have that high side pressure, the pressure entering the expansion valve that we were designed for. We're not moving the volume of refrigerant through the expansion valve and the evaporator, and now everything acts undersized, basically just because the refrigerant pressure has changed.
Yeah.
Anything to add to that, Paul? Okay.
I don't think so. So basically, if I understand that correctly, and my initial question, what is our head pressure? It's basically our high side pressure, mostly in the condenser. And there are concerns with a change in capacity, essentially, of that, right?
Basically, so your condenser capacity gets diminished, not diminished, that actually increases. The condenser becomes more efficient, more effective. It only needs a portion of its surface to actually do the amount of condensing that it would have used the entire surface on a design day. And so then, because it's more effective, it lowers the refrigerant, lowers the head pressure, and reduces the mass flow, entering the expansion valve. And that's kind of what we're going to try. We need to counteract to get our system performance where it was designed. So the first thing that you can do is you can, vary the airflow across that condenser by staging condenser fans. So that would be step one. And that would be, you'd see that in air conditioning systems. It might have to operate in a wider window. But that would be kind of our first stage of head pressure control is cycling fans, reducing the airflow across the coil. And then the next thing, we mentioned it here, is coil size. So on some supermarket or larger systems, we have split condensers, which are basically two equally sized condensers working in parallel. And when we stage enough condenser fans off, and the system configuration would say, okay, now we can split, we can reduce our condenser surface area by 50%. We'll shut off refrigerant flow through that condenser, and we'll now just use half the condenser. So that is a way to reduce the effective surface area of the coil, keep the head pressure up without any mechanical means. But then next, we need to do some additional refrigerant side controls to help keep the liquid pressure entering the expansion valve up close to the operating window.
Okay, yeah. So you mentioned refrigerant controls. I'll jump over this next slide and kind of look at a little bit of an overview of what you just said. So the main purposes here is like you said, condenser liquid pressure. When we see that those dropping temps, the pressure and the mass flow starts to drop. So one of the purposes of controlling it is to control that pressure, mass flow. And that because if you don't control it, we have reduced feed to our expansion valves. We also see potential damage to compressors when that differential gets really low, that ratio.
Right. Correct. Right? Yeah. Yes.
Over on the left side, we have our air side options, and you already mentioned those. We can stage fans. We could do louvers. Would be another way to kind of reduce airflow or dampers. Those have limitations, as I understand, right? As far as what environments they actually are effective in.
Yes.
And especially with those louvers, dampers. I mean, you could see those freezing up, right?
True. The louvers and dampers, they're very, I want to say those are a very old method of adjusting it, but absolutely fan control. Fan controls have gotten a little bit more advanced too with variable speed fan motors. You can just slow the whole thing down, or you can stage them off. But that would be step one. And once you run out of air side options, that's when you would get into your refrigerant size options. That would be the ideal state. There might be a little bit of overlap on some conditions, but for some systems. But then that's where we would say, okay, we talked about splitting briefly there. Again, limited to larger systems with larger condenser surfaces. But the flooding control, those can be used on very small systems and right up to, again, large supermarket systems. Just the sizing of the valves alters, and other considerations based on size. But yeah, the flooding is a very effective way to do it without adding a lot of complexity to your systems. Okay, that's really what we're going to spend most of our time talking about today, is the flooded controls.
Yeah, so let's actually just go ahead and look at a diagram of a flooded control valve system. So we've got some valves doing that. We've got a couple here. Do you want to talk through those, or?
Sure. So what if this was the middle of the summer, our ORI, the angle style valve, the valve that looks like this in the drawing, that valve should just be doing nothing. It should be wide open. That's kind of how we size these valves, is we want to have low pressure drop across the holdback valve, that ORI valve, in the summertime. So again, the summertime, these valves should be doing nothing. So as the ambient temperature drops, and maybe you cycle some condenser fans and so on, but as the temperature drops, the pressure in your condenser is going to start to drop correspondingly. And when it drops to the set point of this valve, it will start to restrict flow entering. So it's called an ORI, an open rise of inlet pressure. So this is an inlet pressure sensitive valve. So it's reacting to the pressure on the inlet side. And as it drops, it will start to restrict the flow to try and only let refrigerant at its set point through the valve. So if you set that valve for 180 PSI, if the system is operating at 200, that system is wide open. that valve is wide open. It's not doing anything. But as the refrigerant pressure starts to drop, when it hits 180, it will start to restrict the flow through that valve to build the pressure up to that 180 set point. And that's kind of how that valve will start to restrict the flow out of it. Now, in order for that refrigerant pressure to build up, we need adequate refrigerant charge. We need additional refrigerant in the system beyond what we would have needed in summer operation. So we need this additional refrigerant because we need something to back up into the condenser. That's where the flooding term comes from. You're kind of flooding, you're putting additional refrigerant into the evaporator the condenser to kind of reduce its effective surface area and give something to build pressure against. So that is the one way that is one of the components that we start to use to kind of build the pressure up. Does that make sense?
Yeah, it does. I think a little backwards, but one way that I find it kind of helps because in this scenario, we're actually, like you said, it's basically a glorified coupling during summer operation, right? It's super necessary for winter, but just open flow during summer. So if that's the normal, then the opposite of open on rise of inlet would be close on fall of inlet. And that's it's not what we call it, but it does help me think of it because it's like, well, it's open here. When the inlet falls, it's going to close, right? That's the basic operation.
Correct. Yes. So now the same configuration of valve is used as evaporator pressure regulators, an ORI, open rise of inlet. It would just have a different pressure setting, the different springs internally. So yeah, if you're going to buy one of these things, for sure, do not take an EPR. You got to be specific on the pressure rating. So don't just replace with an ORI. But this valve alone is not enough to do the work. Right. So we do have to have an additional device to help keep the pressure up as well. So what it is doing, it is backing up and building up pressure, but it may get to the point where it backs it up and it actually doesn't allow enough volume of liquid refrigerant to keep the pressure up on the high side in the receiver and heading to the expansion valve. So we have this differential check valve, the ORD, which this valve will react at the standard ones at a 20-pound differential pressure. So it's a check valve that when the pressure across it exceeds 20 pounds, it will open and vent or dump vapor pressure into the receiver or on top of the liquid in the receiver. So it's trying to pressurize or keep pressure on top of the liquid in the receiver to help with the flow. So that valve will open at a 20-pound differential and it will close when the pressure drops to 14 psi. So it's got about a 6 psi resolution across it. So these valves work in conjunction. They work together to keep the pressure entering the expansion valve up into its operating window. And in doing so, this ensures that there's enough refrigerant volume to do the work in the evaporator and to keep that compressor operating in its design window as well. So that's the benefit of these two components in conjunction. Okay.
Yeah. Okay.
The comment that's kind of listed here on the bottom is receiver sizing is critical. So the refrigerant that is used to flood the condenser is not necessary for operation in the summertime. It's taking up space, so we need a place to store that refrigerant in the design day ambient conditions. So the receiver needs to be sized to match, to at least be able to hold that additional refrigerant required for winter operation.
Yeah.
Okay.
That makes sense. Let's dig a little bit down to the ORD quickly. We'll just look at that.
Okay. Yep. Yeah. So open rise of differential. So it's a check valve that just, when the pressure exceeds that value, it will open and allow flow. So a couple of key points for servicing this type of equipment. So if this valve, the point about always bypassing, something may be stuck in the port. It may be bypassing when it shouldn't be, but note it's that the reason we offer these different ranges is because there may be different pressure drops across your high side components. Okay. It opens at a 20 psi differential. It closes at a 14. So if you had a pressure drop across your high side components through your condenser and the interconnected piping and any lifts or whatever is required, if that pressure drop exceeds 14 pounds, so if you've got a 16-pound pressure drop, the ORD would open at a 20-pound pressure drop, but it wouldn't close because you have a 16-pound pressure drop on a normal operation. So that would be one of those circumstances where a higher differential check valve will be necessary. And that's something to check if you're adding a head pressure control to a system that's already out there, is make sure that you know the pressure drop across your high side so that you get the right ORD to make sure you don't have that problem. This is one of the things that would be evident if you shut the system, if it was bypassing and you shut the system off to do some diagnostics and you turned it back on and it didn't bypass anymore. The valve reset because you don't have you haven't hit that 20-pound differential pressure yet to open the valve up.
Yeah, so that would be one of those where it's not the right setting versus a debris in the port or a valve overheated where it would stay open, just keep bypassing because at that point the valve is compromised.
Correct. And all of these valves, they have their differential rating. There's a sticker on the valve, or it is stamped into the body. So you should know that differential so that you can determine, okay, it's bypassing. It's an ORD 420 and it's 10 pounds across it and it's bypassing. This is not, there's a problem there. It should have been reset at 14 PSI. We do offer those different ranges. They all have that 6 PSI resolution. So if you had a condenser, with a pressure drop of that 16 PSI, we would say jump up to that ORD 425. It'll open at a 25 differential and close at a 19. So that would be one of those ranges that we would vary. Okay.
Yeah.
Make sense?
All right. But so we're here to talk about the proper setting. And while setting in this position is actually just choosing the right valve, the previously mentioned ORI is actually a settable valve, right?
Correct. Yes. So out of the box, our ORI 6s and 10s, they come set for 120 PSI, which is basically a starting point for, let's say, 134A, lower pressure refrigerants. And then there's two methods that you can do out of the box to just get that setting correct if you're trying to install this in the summertime, where your head pressure is exceeding the factory settings of the valves. So we give some guidance here, and this is taken out of our bulletins, our 90-30 series for these.
Please do, yeah.
90-30, 90-31 would have these tables in it. And it gives you what you can do is take that standard setting valve, take the cap off, and then if you rotate the ORI 6 3 turns, it gets you about a half an inch down from the top of the spring housing. You've basically set that valve for a 200 PSI setting kind of thing. Yeah. So there is some guidelines here in the literature to get you started. But we also have some other tables, and that's the table there in blue that gives you the pressure change per turn of return. So 27 PSI for the 6 and 17 PSI for the ORI 10s. So that's the amount of rotation there. Now, a way to you can't really do much when the system is operating above the set point. So if you wanted to set this for 180, if your system's operating at 200 PSI, you're not going to be able to adjust this. You'll have to make that calculation of how many turns to do. But if your system is running lower, or lower to the point where you can adjust it to see what it starts to hold back at, then you can then set this maybe for 200. And then, okay, I know I need to drop it down, a turn and a quarter to get it down to that 180 or 175 range that I want to see it at. Okay.
That's really clever. Actually, I had thought of trying to do that before because that is the difficulty, right? You install this valve, it's summertime, you want to make sure it's set, but it's wide open. But you also want to make sure that you're not getting another call back in the winter because your condenser's not functioning properly, your cases aren't feeding. And so either a calculated setting, or like you said, going to where it starts to shut down, and then once again, a calculated setting off of that point. Calculated off factory or calculated off of starting to close. So
that gives you those reference points, and you'll see at the bottom of those blue tables, we list the A8 and A9 products as well. So those for the larger systems, also factory set at 120. Now the pressure range of your A8 is substantially, it's up to 400 psi. So you can basically do that, adjust the valve till you see it regulating, and then you can count your turns. Those one turn is 70 psi of adjustment. So you can then get that valve approximated very close based on that. Okay.
Okay. So we'll dig into that a little bit because we've talked about setting head pressure controls, and here we've got the ORI and ORD. The ORD, like we said, isn't really a settable. It's selectable, but not settable. The ORI is settable. So, but now we have an A9, and if I pull these up, this diagram, now we have two valve system for head pressure control, but both of these are settable. The A8 is going to be set in the same way that we just talked about the ORI, right?
Yes. Yeah. So because of the range of this valve, you can set it to see it take effect. So, okay, I'm running at 200. I can get this to now hold back at 220. Then, drop at 220. One turn is 70 psi. So one turn of rotation, I can set that for 150. So that would be, where approximately would be. So instead of one turn, I would adjust accordingly to get it to be have a 180 holdback capability there. Then it would return to wide open. It's a little bit more difficult with the A9 because, again, it's a receiver pressurization valve. So we need the outlet pressure to drop. So what our suggestion here is with an isolation valve, you can shut the outlet pressure off, and then using your manifold, connect that pipe, the outlet side of that valve, to suction or low pressure where vapor would have no consequence. Bleed it off till it's below your setting, and then adjust so that it bypasses to build it up to that. And then you've got the outlet pressure kind of set for it's ready to go. Again, if the design conditions are such, you can set it initially, but that would be a way to get a fixed setting adjustment on this valve. And it is, if we go back a slide or two, it is also set, I believe, for 120 as well. The caution with A9s is there's two different pressure ranges. You got to make sure that you get the high pressure range because A9s, an A9 is always an outlet pressure regulator, but it could be a hot gas bypass for smaller air conditioning systems, or in this case, the receiver pressurization on the high side.
Yeah.
Just be aware of that pressure range when selecting that valve or replacing that valve.
Yeah. And I do like this diagram. I'll sit on here for just a second longer because we had those other diagrams, and we'll see a couple more before we're done. And they have the ORI, ORD, and we know their function. We've just talked about those. But I think this does a great job because it actually has, I'm a visual person. This is a condenser holdback valve. Its function is to hold back liquid or refrigerant into the condenser. This is an A9 receiver pressurization valve. Its function is to pressurize the receiver. And these kind of work in conjunction. When this holds back, this picks up to pressurize the receiver, where otherwise would be shutting down because of this valve.
Yeah. Yeah. And you're bypassing vapor. So that A9 is bypassing discharge vapor. No mass, high pressure. So its only purpose is it's not necessarily to mix with the liquid coming out of your condenser, which will be, at that higher 180 pressure because it's what it's throttling to. But it may, in the receiver, the pressures can equalize a little bit. Let's keep that vapor pressure up to push that liquid down to our expansion devices.
That's the exact verbiage that comes to my mind. It's a little bit of a silly image in my head, but you have this. It's putting this. We can see this line of blue, liquid coming in, and if that pushing, I just imagine this A9 comes in and it puts in a higher pressure liquid or higher pressure vapor on top to push that liquid out towards our expansion valves.
Yeah. For a little more clarity, just instead of having that high pressure valve tee into that condensate line, it could go right into the receiver. You're just really pressurizing the receiver. That's just a function of that. It's helpful because our other devices kind of tie into that. For our, now I said the A8s are for larger systems. Our 10s and 6s are especially our ORI 10s, you can parallel those. So instead of jumping up to that A8 valve, you could parallel to 10s. You'd have to adjust them simultaneously, or it'll favor one. You can also parallel ORD valves to get sufficient volume to make sure you get receiver pressurization. And we do have those tools do come up if you use a virtual engineer sizing program that will tell you use two ORDs and one 10 or whatever. Okay.
Well, and to that point, so like you said, you can do them in parallel, but with the ORD, you could actually also do them in series, right? So if I had two 20s and I put them in line, you would have a 40.
Yes. Yeah. In parallel, you don't increase the setting, you increase the volume. In series, you increase the setting.
Yeah.
So it would be, two 20s in series, you would have a 40. Yeah. So if you need, for whatever reason, if you did need a 40, which is odd, but it might be required. Yeah.
Yeah.
Okay. Okay. So those are the two adjustable kind of configurations. Again, the ORI, you don't set the receiver pressurization. That's based off of differential pressure. But in this case, we got it. Now we do offer some other products too.
Yeah. And so I focused on these first because, like I said, we're talking about settings, but with the other options are less settable as well. So we could look at, for instance, a ORA, OROA, or LAC valves, sometimes called LAC valves, right?
Yep.
I don't like that term. They're not lacking anything, right?
Well, LAC, low ambient control, an abbreviation for low ambient control. And the OROA is open rise of outlet. So ORO is open rise of outlet. And that's a key difference between this and the ORI valve, which was sensitive to inlet pressure. So the OROA valves, it's the receiver pressure that's telling this valve whether to hold back and restrict flow leaving the condenser. So this is definitely a little bit of a different control strategy. It's receiver pressure that is your reference pressure here. It functions basically the same, restricts flow out of the condenser to try and maintain that pressure on the outlet side. The OROA valve combines the functions of a holdback valve and that differential check valve. So actually built into the valve itself, I've got an older model here. This portion is a differential check valve. So the high pressure coming from the condenser bypass line, it's the same differential check valve as the ORD. So this works off of a 20-pound differential. And that's what we have different settings. We have the OROA, we have OROA-B. B would have a higher differential check valve, the 25. A C would have the 30, and a D would have the 35. This is a D, so this has got the 35-pound differential. Go ahead, Paul. Sorry.
Well, I was just going to say, agreeing with you, and that's why I actually broke these out separate, where we have this is an actual combination of function in the ORI and the ORD, whereas this. It serves the same purpose, right? It's still going to be this head pressure control in one valve, but it does not have integral or like internal attached check valve to that, where especially the sample you just held up literally just has attached to the side of it that same ORD type check valve.
Correct. So the OROA has that 20-pound deadband. Like, it's not going to bypass unless the pressure drop across its port exceeds 20 psi, or whatever the setting is. The LAC valves, as soon as it deviates from its set point, it will allow some hot gas to bypass. So they're a little bit more, and they have different sensitivities. So what I mean is the LAC valve, it's actually reacting to the discharge pressure. Sorry, LAC4, the small one. The LAC4, it's the discharge pressure. So if it's a LAC4 180, as the discharge pressure drops below 180, it will start to restrict the flow leaving the condenser and allow hot gas to bypass to pressurize. The LAC 5 and 10, they, like an OROA valve, they react to the receiver pressure. And as the receiver pressure drops, it then would start to restrict flow from the condenser. So in both cases, they're all trying to restrict flow from the condenser. Every one of these, to function properly, requires the additional refrigerant to flood the condenser. So that alone, these valves won't do the job. That additional refrigerant is required to make these valves function.
Yeah, and just to kind of clarify, because we've used that term flood the condenser.
Yeah.
I know when I started in this industry, that was kind of a weird term to me.
It
But
is.
like we said, we're holding back that refrigerant. And so if we think of it that way, it wants to basically stop being full of liquid, right? It's just,
Yeah,
or
we're just trying.
stop being full of
Yeah,
refrigerant. And so we're
yeah, we're
holding
trying
it
to.
back. We're making sure it actually stays in there and builds some pressure in the condenser.
Yeah, yeah. We need
Yeah.
the pressure to help build. We need the refrigerant to help build the pressure up. Yeah.
Yep.
And then
And we, for me personally, maybe there's someone else out there, this weird verbiage of stacked liquid, that helped me understand. It's stacking liquid back in the condenser. It's
yeah,
it's making sure it builds up in the condenser before it can come out. And we see that in the pressure.
yes. The pressure is key. I mean, it's got to be liquid. We still have to. It's got to be 100% liquid going
Yeah.
to that expansion valve. But without that pressure, we don't have the force, and we're not moving the volume. So it's not that, like when we say, oh, the TX valve will act undersized in the wintertime without adequate head pressure control, the valve sizing is the same. The refrigerant has the same net refrigerating effect, same BTUs per pound. We're just not moving the pounds. We don't have the pressure to move the volume. We need to get that pressure to move the volume to do the work and keep that load and compressor happy.
Okay. Another, I guess, a good point since you brought that up. Here we say expansion, we say thermostatic expansion valve because we're spoiling, right? You could say expansion device is another. If I'm drawing a generic, refrigeration system, I might write. But another one I've also seen and written myself is pressure drop device, because that's really the point of the expansion is the pressure drop. So to your point, you said we need that pressure. We need liquid as well, because that's what's going to boil off in the evaporator. But if we don't have pressure drop, if we can't get pressure drop, even if you have liquid, if there's no pressure drop, you're not going to get that desire for expansion and boiling that you would see, right? We need inlet pressure high enough so we can see a satisfactory drop through the expansion device and evaporation in the evaporator.
To get that volume. Yeah.
Yeah.
Okay. So the next slide, I think, is the one. We just want to kind of show this. So this is actually just looking at the piping diagram, this is the LAC valve. And you don't notice a lot of differences, but except for on the outlet side, we show a check valve. And that's because if you looked at the OROA, it has a check valve in that hot gas line. So it's not going to allow refrigerant flow backwards through that hot gas line. So that's the same as just using the straight ORD 420. And the other pathway is completely through the condenser if refrigerant was to migrate in the off cycle. The LAC, as soon as it's off its set point, it can open that pathway from the receiver right down that bypass line to the compressor. So that check valve is there to prevent off cycle migration back to the compressor. Okay, so now I'm under the assumption most of our manufacturers that use the LAC either use this or they've taken that into account in their condensing unit and have a provision for addressing that. So just keep that in mind. Okay.
And then on here we have some other just general troubleshooting that would cover both the OROA and the LAC valve, the line valve. And so, and I put this diagram down here because I find it helpful if I'm looking at a problem, and I'll do this if I'm working on a system, I'll draw a sketch on the back of my notebook or something like that, so that I can actually visualize what's happening. So if we say there's no refrigerant at the expansion device, where obviously it's on the screen, low charge. What makes you say that?
Well, it would be that we're not getting the mass flow. So so often if you don't have enough refrigerant in the system, most refrigeration systems operate on a pump down control. And if you energize a solenoid to allow refrigerant to flow into the evaporator, well, if there's not enough pressure drop, you can energize that solenoid and, think about it. Sometimes your ambient conditions are colder than your evaporator. If you don't get the refrigerant to flow, you're not going to trip a pressure switch and bring your compressor on. You've got everything is matched, but you don't necessarily bring it on so that low refrigerant charge. So not having that flooding capacity to keep that pressure up will prevent that flow. So you're not going to see the refrigerant of the TX valves. It's not necessarily that you're going to see bubbles, which you may if it's a bypass problem, but ensuring that you've got sufficient refrigerant charge is key. And it's hard to do because most receivers on small capacity systems do not have a level indicator. So you've got to work off some assumptions there. Sometimes you've got to pull the refrigerant out. So when I kind of as a service kind of tip, you pull refrigerant out until the sight glass starts to bubble. Then you charge to the clear sight glass. So now you've got an operating charge for that day. Then you've got to calculate how much refrigerant is required to flood that roof, flood that condenser completely full. Then determine on your coldest day how much needs to be flooded. So it might only be 80%. You might only need to flood that condenser 80% on a cold winter day. But depending on you can also calculate how much of that condenser is flooded if you're charging it below, let's say 70-degree ambient, using our calculation tables. You can say, I'm charging it today and it's 40 degrees outside with my valves already set. 40% of that condenser is already flooded. So if I only need 80% of my condenser flooded, I'm already 40. I only need to add 40% of the total flooded charge to get back where I need to be. Make sense? I covered a lot in a sentence there. So sorry. I think we're kind of running up on the time, but that's that charge thing. So the charge is critical for these valves to do their job. Everything can be properly sized, but without that extra refrigerant, it's not going to have the effect that you want to see. That comment about high condenser pressure, well, that's that consequence of that charge. What you may require to build the pressure up in the wintertime, now your receiver doesn't have that holding capacity and you've got to get that refrigerant out of the system or size your receiver properly or whatever countermeasure is necessary to address that. And then our valves are, they do have diaphragms in them. So just kind of a key thing, like with one of these valves, if you take this cap off to adjust it and you get pressure coming out of here, even if it just goes, that's an indication that the bellows have been compromised. So that valve should be replaced, right? Like if it's just a little something, maybe due to ambient conditions, but yeah, don't leave the cap off, put it back on because you don't know how close those bellows are to completely rupturing, and then head to the supply house and get a replacement. Then with most of our other valves, like the OROA and the LAC valves, if the diaphragm is compromised, that is the force that the condenser pressure is working against. So if that's compromised, it basically just goes straight flow out of the condenser. It won't hold back. So that's an indication you won't build your head pressure up if those things are compromised.
Yeah, and that's where we see this constant bypass, right?
So natural pressure drop exceeds the differential check valve. So that's where the valve would be continuously bypassing. And stuff in the port, obviously, I mean, that would cause all of our valves to bypass when not required.
And I do want to bring up a point, this valve overheated. So because we brought that up again earlier with ORD. So I think the main point here, and a lot of people know this, is not a concern of system pressure overheating it necessarily, though that could potentially happen if there's something else wrong in the system. What we're specifically talking about is installation overheating. And we see that sometimes with those ORIs because, like he said, there's those brass bellows like inside the valve. And if I just burn that valve while soldering it in, that's where we're going to see more likely that as the valve cycles and those bellows move, that we fatigue and crack those bellows.
Yeah, you reduce the longevity. And another point is if you've got a system that has a bad condenser fan, especially a single fan condenser, if it's a single fan condenser and it's going off and on and off and on and off and on, the diaphragm in this valve is going to be up and down and up and down and up and down. As those pressures deviate, you'll prematurely wear out the head pressure control. So catching those things, addressing those problems, head pressure control fluctuate, like things that aren't working can cause system pressure fluctuations. Those can lead to diminishing the life of not only this valve, but the other bellows style as well.
Yeah. It's interesting you mentioned that because in my previous life, I worked in R&D, I worked in the lab, and we did that on purpose. We called them life cycle tests, and we would try to, take a valve and okay, what is its projected life? Can we achieve that in a month? And that's exactly what we did to those valves. So if you wanted to age your valve, 20, 30 years in the course of a month, that's how to do it.
Yeah.
So not recommending that. That's how we calculated all that in R&D. Well,
Okay.
let's mention, so all of these so far have been mechanical, and it is worth mentioning that we do have electric options if you wanted to do these head pressure control with electric options. Though it comes both in the form of A8 and A9 conversion kits, so we can see that pictured here.
Yep.
So obviously you'd have to pump that down, but you could just unbolt the mechanical control on top and replace it with this 42 millimeter motor.
Correct. And also for our old legacy ORI and CRO head pressure controls, they've been obsolete for 20 years, but the body is still the same. And we have conversion kits that can work in those as well, plus the new CDS and SDRs. So we do have capacity tables for those for vapor flow and for liquid flow. And so you can size it up, but that's the thing with these valves is they have no logic in them. They do not know what they are. You need to program, you need to have a controller that tells it what it's supposed to do and what its parameters are. We do have controllers. We've got a pressure controller and a temperature controller, but that, more integration in some other devices may be a better approach. Fundamentally, they're going to do the same job, still require that flooding charge. So we're not necessarily addressing that, but we are automating it a little bit. So maybe you can have variable set points as opposed to fixed set points in this case.
And I've said, because people will argue, well, what's better, electronic or mechanical? And I think a lot of it boils down to, what do you want to work on? If I've known guys who they felt a lot more confident in turning an adjustments knob and saying, okay, I've set this valve to this pressure. And I've known other guys who said, I'm really confident at finding the right sensors and the right controller, hooking all it up, running some wires, and then plugging in a pressure and saying, here's the pressure I want you to start closing at. And it's a preference, right? If you feel more comfortable with, pressure set points on a controller, it's functionally doing the same thing.
Yep. Yeah. No. Again, also more things to go wrong. So you've got the communications and your sensors and your other devices too. But yeah, there's benefits there. Again, you could shut this valve off remotely if it was bypassing and it shouldn't be. There's that capability. So
you can shut this valve off remotely, but it might not have the same zero positions of a mechanical valve if you lose power.
Yep.
So pros, cons, both sides. You can make your decisions on what battles you want to wage, and then just because we've mentioned it multiple times, that flooded condenser and those calculations, we do have, and this is, you can see up there, 930-1 would be the charging recommendations. So if you wanted to calculate some of that, right, this is what you would be looking at.
Yep.
And
so
I think
you need to know,
Go ahead.
And you just need to know your design conditions for your coldest day of the year. You basically you calculate the total flooded capacity, what that with your refrigerant type and your conditions, that is going to hold 100 pounds of refrigerant. Then you then correct for the coldest day of the year you're going to see in that area, which might say you only need 90% flooded. So that would be the value that you would use to charge to. And then again, you can correct for the time of year when you're doing some charging. You can make that calculation too. This would be a whole presentation in itself, how to run through this. So it's online, it's available through Sport and Literature, and good thing to add. Okay.
So that's actually the last of my presentation slides. I'm going to just bring up one thing as we go into questions, because the first question we have is, and I say question, it doesn't have a question mark on it, but it says, well, I guess the question was, will there be different pressure settings for the A2L refrigerants? So, and then saying R454A is the most common A2L. So if you're setting those, charging those, that would come out of this book here, right? Where you do those calculations.
So this will give you the guidance for how much flooding to put on the roof. So how much additional refrigerant is required to do the flooding. As far as the pressure settings go with your condensing unit manufacturers first. So we've got to kind of deviate a little bit, because there's the AWIF compliant small condensing units that would use the small A4s, they would have a lower setting, which is kind of mandated to get the efficiency. So instead of having like a 180 setting, they might only have a 150 setting, and that's to lower the BTUs per watt, the efficiency of that unit. So what dictates your pressure settings is your design ambient conditions and the pressure, the saturated pressures at those conditions. So that's where, so you can pretty much determine if we're going to be working at 90-degree condensing, I should have mine set for a pressure corresponding to that. So, our factory set, like the 180 is a fairly common setting for, basically the R22s, the 404s, and 448, 449 are very similar. So that kind of would be where we would typically be just as a starting point. But yeah, check with your condensing factors on that.
Yeah. And the only reason I stayed on this slide was because when it comes to this image I have here, as the slide maker, I did a not good thing, and this is an old image. So this says 2012, and I believe we've actually last updated this document in 2024, and it does have those 454s that you would be looking for in that. So I'll just go to this next clean slide, and we'll answer a few more questions.
Okay.
So we have this question. If the A9 is putting out vapor, how are you getting solid column of liquid at your TXV? I think we kind of answered that.
Yeah, the A9, the intent is, and that's kind of, I prefer a diagram that just shows the A9 going into the receiver. It's just putting vapor on top of the liquid to bump that pressure up on top of the liquid. We're still getting liquid coming down our condensate line from the condenser at, it should be at that pressure. I mean, it's holding back.
Yeah.
Obviously there'll be some pressure change, but we want liquid. It'll probably be pretty subcooled too, but you lose a bit of that in the receiver. But yeah, it's not intended to mix. It's not intended to mix with the liquid. It's intended to pressurize on top of the liquid.
Correct. And even if it was teed in like that, it's on the inlet of the receiver, not the outlet, right? So what we're seeing is at that point, you're talking about the function of a receiver versus the function of an accumulator. So that receiver, if functioning properly, it has liquid in it stacked up in the receiver as well, and it should only be sending liquid out, right?
Yep. The tube should be at the bottom, and it should just be pulling the liquid. Yeah.
As long as there's pressure in there to push the liquid through, which is what the A9 is there for.
There you go.
Next question says, is there any risk of hot gas coming out of the A9 causing the liquid coming out of the A8 holdback valve to boil and violently expand? So causing expansion kind of where they meet.
I've never thought about that. I don't think so. You're dealing with different densities too, right? So that might be
But I think that's kind of what we're talking about, is the goal isn't to mix, but they will mix a little bit. And if they're set properly, there shouldn't be violent expansion. You're not dumping in too much.
And it's not contained. It's not contained. It's it's not like there's, if everything was in isolation, and you're traveling at different velocities too, right? That discharge pressure is going to be dumping in and whistling through there. So this is not a new process. So this has been like this, as to the date code on this is 1976. So this valve's 50 years old. Hasn't, been a pretty proven method. Yeah.
All right, we'll answer a couple more questions here. We have one that just says how to set A9 again, please. So I think actually what I'll do for that person is I'm just going to back up a few slides. And so this is a 3-point set on how I would adjust an A9. And so we can run through it pretty quickly, but what we said here was you'd close this ball valve, right? So now when it flows through, it dead ends and it can't pressurize anymore. Yeah.
And then you need a service port on the outlet side of that A9 somewhere. And then you would connect your manifold set to a low pressure low side of the system so that you can vent that refrigerant off, right? You don't want to dump it into the atmosphere. You just want to be able to bleed it down. So you would bleed that pressure off and then adjust your A9 to then repressurize that you're simulating, I guess, the receiver with that little space. So it's sensitive to outlet pressure. So when that outlet pressure drops, you would set that to the receiver pressure you want to maintain, and then bleed it off, reset it again, make sure that it only pressurized to your 150, and then shut off, or whatever you're trying to set it to, 160 in this example. And conversely, if your receiver pressure is lower than your set point, I mean, you can just adjust accordingly. You don't need to do the shut off. This is really just for setting it up in a time frame that's not possible. And if you go back a couple more slides, we do got that table. So out of the box, it's set for 120, and then there is some adjustment. I think I've got it here, 25 psi per 100 for a rotation. So if you adjusted that valve one turn, you're going to get it up to that 150 set point.
Yeah.
Or 145. Yeah. So I'll put there. Okay.
So and the key point there is this is a pressurization valve. So if I closed this off, or if my receiver was lower, this is all it's doing is adding pressure. So if it's pressurizing this section of line to 160, it's going to do its best to pressurize the receiver to 160 once I open up this ball valve, right?
Correct. Yep. Because it's reacting to its outlet pressure, and that would be it. Yeah.
All right, we'll do another question or two, and then we'll probably let these fine people on their way for the week. And questions that we don't get to, we can respond to. If you've registered for this, we can send out responses as well. So, but going back to questions, do you recommend or not a fan cycle on a single fan condenser when using a flooded head pressure valve?
No, don't cycle a fan. Now, because of what you're going to see in that pressure is going to deviate. It's going to go up and down and up and down if you're cycling a single condenser fan. Now, can you vary that speed? I'll let the condensing unit manufacturers make that determination, because they may have a strategy for varying the speed of that single fan down to a lower limit that doesn't see the abrupt changes in pressure. But it's the changes in pressure that are the concern for us. The condenser manufacturers might have another concern about the expansion and contraction of tubes on the header. But no, don't cycle a single fan. Always have at least that one fan running to keep stability in the system pressure. Yeah.
And then we'll do one more, the last one, and then we can let everyone go. So it says the ORD is a 20 psi differential valve, but will not start opening till 16 psi of differential, and will close again once pressurizing the receiver to 16 from discharge. Question mark. So we'll go up. So they're basically they're go ahead.
So it opens at 20 and closes at 16. That's at 14. That's that 6 psi of resolution. So it takes the 20-pound differential to get it off its seat. And then as it builds up pressure on the outlet side, it'll close when it gets to 14.
Yeah.
Okay. That makes sense. And that should,
a little bit confusing, but that should be kind of visible down here where it talks about where the window where it kind of opens and closes. So
yeah, it's all that 6 psi window of opening, 20 to open. But then if you don't want to just doing this, open, close, open, and then close at that with that differential change.
Yep.
Okay. Now I can't see that on gauges. I mean, it's either bypassing or not. When I was doing the service, because it happened, but just be aware of that difference. The concern was, I did do, this is when I was a Sporlan, I did do a technical call where, all your ORDs are no good because they continuously bypassing. And we went there and found that, the pressure drop was too high. It was just bypassing because the condenser pressure drop was high. So they had to go to a higher setting valve, but that was just something that they never checked. So keep that in mind. Avoid a problem. Okay.
All right. Well, thank you, and I'll hand it back over to John.
Right. Super helpful information today. I just want to thank you all for joining us for our webinar on the head pressure controls. We hope you found the information valuable and can take a couple nuggets of wisdom with you to your next service call. Special thank you to our presenters, Mike Pod and Paul Chambers, for sharing their expertise and insights. Remember, you'll be receiving a follow-up email with the resources discussed today, so keep an eye on your inbox. We appreciate your participation and engagement. If you enjoyed this session, we invite you to join us for our next webinar, where we will be exploring some of the new technologies that we've developed for refrigeration and HVAC controls, specifically our new MT1 system. Stay tuned to our social channels. Next month, Paul will be sending out some interesting clips from the AHR Expo in Las Vegas. If you want to circle back on this information, we have recorded today's presentation. Navigate to the Sporlin YouTube channel. You'll find a library of videos highlighting our products, some basic and advanced topics. Thank you once again, and we'll see you next time.
All right. Thank you.